In this section, we'll talk about an application of differential equations called compartmental analysis. Many complicated processes can be broken down into distinct stages, and the entire system can be modeled by describing the interactions between various stages. Such systems are called compartmental and are graphically depicted by block diagrams. In this section, we will look at two basic examples of one compartment systems. And the basic differential equation for this type of system is dx dt is the input rate minus the output rate, and it can be schematically represented as follows. We have some kind of quantity, there's stuff coming in, and there's stuff leaving. So one such example is a mixing problem, and we'll do an example here. So consider a large tank holding 1,000 liters of pure water into which a brine solution of salt begins to flow at a constant rate of 6 liters per minute. The solution in the tank is kept well stirred and is flowing out of the tank at 6 liters per minute. If the concentration of the brine entering the tank is 0.1 kilograms per liter, determine when the concentration of salt in the tank will reach 0.05 kilograms per liter. Okay, that's a lot of information. But let's try to break this down step by step. So we're going to define our function x of t. X of t will denote the amount of salt in the tank at time t. Now, eventually we'll have to worry about concentration. Concentration can be calculated as follows. The concentration is amount of the substance, in this case salt, over the volume. So that's an extra step that we'll have to take in the end. Okay, now we're going to have to set up a differential equation for this system. And one of the first things that we can notice here is that we have x of 0 is 0. So this is our initial condition. So that part is the easiest part right there. That's our initial condition. X of 0 equals 0. Now, we saw that a system like this, the differential equation that we set up is dx dt equals input rate, what comes into the system, and then minus the output rate. So what is the input rate? Well, we can break the input rate down into two components. It's the input flow rate. How fast is the water coming in? Times the input concentration. So what's the concentration of the salt coming into the tank? And then we subtract from that the output flow rate times the output concentration. Okay, so now we have to figure out what are these rates and these concentrations. So the input flow rate is 6 liters per minute. I'm going to write 6, and then I'll put the units in here, which is not strictly necessary, but I want to show you that this makes sense. So it's liters per minute. And then the input concentration is 0.1 kilograms per liter. So we multiply this by 0.1. Input concentration was in kilograms per liter. And then from that, we subtract the output flow rate. How fast is the water flowing out? So that's 6, and that's also in liters per minute. And then we have the output concentration. Now, that is not given here, right? We only have the output flow rate that's given here. So the output concentration, we have to look at concentration is the amount over the volume. Now, here we have a volume of 1,000 liters, right? So this is the volume of the tank. And note that that volume is constant because water's coming in at 6 liters per minute, and then water's leaving with 6 liters per minute. So the volume is constant. So we know that the denominator here is going to be 1,000. Now, then we need to look at what the numerator is of this expression, and that's the amount of salt in the tank, right? And we called that x of t. So what we have here is we multiply this by x of t divided by the 1,000, and that's again going to be in kilograms per liter because x of t is the amount of salt in the tank, and that will be in kilograms. And then we have the volume that's in liters. So maybe that's a good thing to write here, that this is the amount of salt in kilograms. Okay, so when we combine all of this, what we see is that liters here and liters here cancel out for the units. So the units here are kilograms per minute, and here it's also going to be kilograms per minute. And then what we have for our differential equation is the following. It's dx dt equals 0.6 and then minus 6 times 6 over 1,000 times x of t. And the units, as mentioned before, are kilograms per minute. And that makes sense because X is a quantity that's expressed in kilograms, and T, that's time, which is measured in minutes here. So the rate of change will be kilograms per minute. Okay, now this equation here that we have right here is something that we can solve with the methods we discussed in chapter 2. So take a moment and try to figure out what type of equation this is. Is this a separable equation? Is this a linear equation? Or is it neither? Well, it actually turns out that this equation is both linear and separable. So the way I will solve it is as a separable equation. And then what you could do is you could look at this as a linear equation and solve it that way and see if you can find the same answer. So let me write down the equation. Let's simplify it just a little bit more. So I have dx dt equals 0.6 minus 0.006x, right? And what I see is a function here that depends only on x and not on t. So I can bring that to the other side and then multiply both sides times dt to get everything with t on the other side. So what I get after this is the following. So I can rewrite this as 1 over 0.6 minus 0.006x dx equals dt. I can think of that as 1 times dt, and that's a function that depends on t only, or said slightly differently, that's a function that does not depend on x. So we can integrate that. So now our next step is to integrate both sides. So I'm going to take the integral on the left, integral on the right. And I'm going to skip the step here where I'm going to do a substitution in the interest of time to not make these videos too long. You would use a substitution u equals 0.6 minus 0.006x and then integrate that. But like I said, in the interest of time, I'll give the solution to the integral here. So that's negative 1 over over 0. Let's clean that up. So over 0.006 and then times ln of the absolute value of 0.6 minus 0.006x. And then on the right-hand side, the antiderivative of 1 is t, and then we have a constant of integration. We have one on both sides, but as discussed before, if you have a constant of integration here, you can move it over and that's your constant of integration. Now, let's call this C1 because we're going to play around with that constant of integration a little bit. So the first thing that I want to do when I want to solve for x here is to get rid of this negative 1 over 0.006. So I'll multiply both sides by negative 0.006, and I obtain ln of 0.6 minus 0.006x equals negative 0.006t plus, and then I multiply a constant times a constant. That's a new constant that I'll just call C2. Okay, and then to get rid of the ln, I exponentiate with respect to e, right? So I would do e to the power ln, that gets rid of my ln, and then I have the absolute value of 0.6 minus 0.006x, and that then equals 0, or e to the power negative 0.006t plus c2. And then to get rid of the absolute values, I put a plus or minus there, right? And I'm going to rewrite the right-hand side slightly different. I'm going to write this as e to the power c2 times e to the power negative 0.006t. And then I have a plus or minus that comes from getting rid of the absolute values here. So again, this, whether it's positive or negative, e to the power c2 is a constant. So I'm just going to call that c. Okay, now let's continue this over here. So we're going to move to the top right here, and we get 0.6 plus c times e to the power negative 0.006t, and then that c goes to the other side, or that went to the other side, and so the x goes to the other side, and so we have that's equal to 0.006x. Then finally, we divide both sides by 0.006 to get our x, and 0.6 divided by 0.006 gives us 100. And then c divided by that gives us another constant, e to the power negative 0.006t, and that gives us x of t on the right. And that's our general solution. For remember that x of t stood for the amount of salt. Now, to figure out what k is, we need to use our initial condition. Right? So our initial condition was x of 0 equals 0. There was no salt in the tank. So that is t equals 0 and x equals 0. And if you plug that in here, then you get you get 100 plus k times e to the power negative 0.006 times 0, right? That's the t. is equal to x of t, and x is 0. So we plug in 0 here and 0 here. E to the power 0 is 1, so you get 100 plus k. So we get 100 plus k equals 0. So our value for k is equal to negative 100. And so our final solution for our function x of t equals 100 minus 100 e to the power negative 0.006t. Now, that's not the final answer to our problem, but it's important enough to at least put a square around this because this is an important result, but it's not our final answer. So let's take a look at what was the final, or what was the question asked here. It was determine when the concentration of the salt in the tank will reach 0.05 kilograms per liter. Now, concentration is the amount over volume. So we want, so the question that is asked here is, when is the concentration equal 0.05 kilograms per liter? And so what we have to do there is concentration is the amount x of t over 1000, which is the volume. So this is my concentration, x of t over 1000, right? It's the amount over the volume. The volume is constant, so that's the concentration. And so that has to equal that 0.05. Or equivalently, by multiplying both sides times 1000, you have to solve x of t equals 50. So now we have our formula here. And from this point out, it's algebra. And that's 50. So we subtract 100 from both sides, and then we get negative 50. And so this is equivalent, and then we can divide by negative 100. And so this is equivalent with e to the power negative 0.006t equals 0.5. And we can isolate the t by taking the natural log on both sides, and then we divide by 0.006. So this is for you to check that last little step, but what we get is that t is approximately equal to 115.52 minutes.